Okay, so we were talking about the membership functions. So the membership functions are of a certain type. So this is shown in this figure. So you will get a membership function in this way. So let us look at all the various parts or the properties of a membership function. So first of all, you have what is called the core of a membership function. The region which has full membership. So all those elements where the membership is equal to 1 is called the core. Okay. The core could also be a empty set. Okay. So in this figure, this will be the core. All these values come in the core. Now if you didn't have any of these values, it could be you may not have even one value in the core basically. The second one is what is called the support. So this is the region of universe that is characterized by non-zero membership value. Okay. So we call this the support. So the set of elements which are there from the universe of discourse, such as x1, x2, say up to xn, that together is known as the support. So this is your support. So the points or the elements which have non-zero membership function. So they have a membership function which is greater than 0. If the support is a single element, it is called a fuzzy singleton. That means you have only one element with mu a equal to 1. Then you have the boundary region. So the boundary region is from the support. If you remove the core, then you have the boundary region, that is the elements of X which have membership value which is less than 1 but greater than 0. Okay, so this will give you your boundary region basically. Then if we come to if you don't have, if you just have if you have at least one element which has a membership value of 1, okay, it's called a normal fuzzy set. So here this is a normal fuzzy set because it has some points which have membership of 1. So here also we can see that this set has one single point which has membership of 1. So we can call this as a normal fuzzy set. Whereas a subnormal fuzzy set doesn't have even one element which has a value of 1. Okay. So such a fuzzy set is called a subnormal fuzzy set. So we can see this is a subnormal fuzzy set because the largest membership value of this fuzzy set is less than 1. Okay, so that's called a subnormal fuzzy set. Another concept we can talk about is the convex and the non-convex fuzzy sets. So here this is called a convex fuzzy set and this is called a non-convex fuzzy set. So convex fuzzy set has membership values which are increasing, or it has values which are decreasing, or it has values which increase and then it decreases. Okay. But if it is not any one of these, it's known as a non-convex fuzzy set. So here it increases, decreases, again increases and decreases. Okay, now if you take three values like x1, x2, x3 in these three, right? Any values where you take first x1, then you take x2, then x3. This should work for any set of values. So what you find is that the membership value of the second value, if it is greater than or equal to minimum of the first and the third value, then it is a convex fuzzy set. Otherwise, it's a non-convex fuzzy set. So, if we take this second one, it doesn't really work. Okay. So, if you take the membership value of the middle one, it's not greater than the membership value of the other two. So, this is not a convex set, whereas this one is a convex fuzzy set. And then we have the concept of height. So, if we take the height is the maximum membership value that you have is called the height of your membership function. Okay. So, the maximum value that it can take is 1. Okay. So, if you have a normal fuzzy set, obviously you have at least one point which has a membership value of 1. So, the height will be 1. But if the height is less than 1, then it is a subnormal fuzzy set. When the fuzzy set is a convex single point normal fuzzy set, then it is termed as a fuzzy number basically. Okay. So, these are some definitions which we have to see in the membership functions. So, basically when you are going to work with the fuzzy values, you need to sometimes convert a crisp set into a fuzzy set. Okay, so what you need to do is you need to take the problem, convert it into a fuzzy problem and solve it using fuzzy sets, and then defuzzify it and give a crisp answer to whatever you are looking for. So, first what needs to be done is that the fuzzification needs to be done. That is, it's the process of transforming a crisp set into a fuzzy set. So, it converts the crisp input values into linguistic variables. Okay. So, you may have for example, somebody's height is say 5 feet 5 inches, maybe you have to convert it into height is equal to medium or small with some membership function, etc. Okay. So, suppose you have something which says it's 9 degrees centigrade, right, and you may have to convert that into hot or cold or medium or whatever you want to convert it into. So, how do we find the membership value assignments? So, there are a number of ways in which we do it. I will not go into the details of that. So, first one is by using intuition. So, if you take something like height of a person or the temperature, etc., you could just use your intuition. You know what is cold, what is hot, or what is tall and what is short, etc. So, you could use that to form your membership function. Another way is to do some type of inference and then use it. You could also use things like neural networks to actually get the membership values that you are looking for. You can use rank ordering in some way, right? So, you can order those points in a particular order, and then you can say that you can start with a lower membership function and keep increasing the membership function at regular intervals. So that is one way of doing it. So, for example, if you have say 5 temperatures or something, you could say that you will take the lowest temperature maybe as 0.2, and then you take the next temperature as 0.4, 0.6, etc. So, you could do some type of rank ordering, and depending on the rank ordering you can fuzzify it or get a fuzzy membership value. So, basically you have to take the attributes and convert crisp set into a fuzzy set basically, and for individual values you may of the attribute you have to get the membership value by using that basically. Okay, then we have the concept of a lambda cut. So what is it that you are doing in a lambda cut? So basically what you are doing is you are taking the fuzzy set, and from the fuzzy set you are deriving a crisp set. Okay, so you could say that is some type of defuzzification that is being done. Okay, so what you are taking is you are taking the fuzzy set A and you are converting it to a set A lambda. Okay, and this A lambda is called the lambda cut or the alpha cut. You could also use alpha here instead of lambda, and this is a crisp set. Okay, it's a crisp set which is derived from the fuzzy set basically. So how do we define it? So A lambda is equal to x such that mu A of x is greater than or equal to lambda. So you are taking lambda to be some membership value between 0 and 1, and you are saying that all the points who have membership value which is equal to this or greater than this will be there in the A lambda. So A lambda will consist of a set of elements, okay, which is a subset of the elements which is found in set A. So the set A lambda is called a weak lambda cut if it consists of all the elements whose membership functions are greater than or equal to as given here, right? So this is called the weak lambda cut. But suppose instead of greater than or equal to, we just keep it as greater than, okay? That is known as a strong lambda cut. That means the membership value have to be strictly greater than the lambda which we are talking about. Okay, so a strong lambda cut is given by this thing. So it's greater than lambda basically. So if we take a lambda cut set, okay, that is a crisp set, and if you take for a particular fuzzy set A, if you see all the lambda cuts sets that you can get, it will form a family of crisp sets. Okay, so A lambda is a crisp set. So you can transform a fuzzy set A by using lambda cuts into a infinite number of crisp sets basically. Okay, so what are the properties of this lambda cut sets? So suppose I have two fuzzy sets A and B, so I am taking A union B and taking the lambda cut of that, that will be equal to the lambda cut of A union the lambda cut of B. Similarly for the intersection, A intersection B, the lambda cut of that is equal to lambda cut of A intersection the lambda cut of B. And this one is not equal, right? So that is you are taking the A bar and finding the lambda cut of that, and that is not equal to finding lambda cut and taking the A bar of that. So if we take two cuts, say lambda and beta, okay, where beta is between 0 and 1, just like lambda is between 0 and 1, okay, and lambda is less than or equal to beta, okay, then you will find that A of beta, so the crisp set A beta will be a subset of the crisp set A lambda, where A naught, so A naught is where your lambda is equal to 0 will be equal to the universe of discourse X. So we have here a figure where you have a membership function with triangular membership function. So if we take a lambda cut say 0.5, okay, you will get it like this, okay, and you find all the values which are greater than that will be members of A 0.5, and if we take A 0.2 you will get this value. So you find that it has more number of elements than if you take A is equal to 0.5. Similarly, you could also have a lambda cut for a relation. So if we have a relation R between the universe X and universe Y, and so you get mu R xy, okay, that should be greater than or equal to lambda, okay. So what is it that you get as R lambda? R lambda is a crisp relation, okay. So it will be a matrix which will consist of zeros and ones basically, okay. So since R is defined as a two-dimensional array, any pair xy belonging to R lambda belongs to R with a relation greater than or equal to lambda, okay. So if we take two fuzzy relations R and S, so R union S, lambda cut of that will be equal to lambda cut of R union lambda cut of S. Similarly, that's the same thing which holds true for the case of fuzzy sets, also holds true for the fuzzy relations that we have basically here. So if we look at these problems over here, so these are actually taken from the soft computing book by Shivanandam and Deepa. So here we have a relation given to you, okay, you have A and B and two sets A and B, and here they ask you to find lambda cut where the lambda value is 0.7 for A, similarly for B where it's 0.2, and then you have to find A union B, and then lambda cut is 0.6, etc., right. So here in the first case you want lambda cut is 0.7 for A, right. So first of all you have to find A bar, right. So A bar will be the 1 minus these values, so 0.8, 0.7, 0.6, 0.3 and 0.9, and then you have to get a lambda cut of 0.7. So when you take 0.7, only those which are 0.7 and above will go into this crisp set. So the three that go into the crisp set are x1, x2 and x3, x5, okay. Similarly you can do that if you take B here, okay, it says 0.2, so all the values will come x1, x2, x3, x4, x5. Similarly for C you find A union B first, and then you find the lambda cut of 0.6, so all those which have membership value above 0.6 will go into this, etc. Okay, so here you take A intersection B and then find the lambda cut, etc. So here you are taking A union A bar and then you are finding the lambda cut of that, etc. Okay, so these are all very easy to do, right. Okay, so here we are talking about the fuzzy relation. So we have a fuzzy relation say between x and y, okay, and find the lambda cut relation for lambda is equal to 0, 0.1, 0.4 and 0.8. So first one is, it says 0 plus, that means greater than 0. but there are two zeros here, or whatever is 0 here remains as 0, all the others will be 1. And when it is 0.1 greater than or equal to 0.1 is what you have to see. So this is what you will get for that. Okay. So if you take 0.02, since it's below 0.1, you will get 0. Then 0.4, 0.8, etc. So finally, you can see that your R lambda, which you are getting here, that is the relationship, crisp relation, is a matrix with zeros and ones basically. Okay, next we will look at the defuzzification methods. Okay, so once you have carried out fuzzy inference in some way, you will get a fuzzy value, okay, so as your output. So that fuzzy value has to be converted into a crisp value. In other words, you have to take a fuzzy set, convert it into a crisp set. You may have to convert a fuzzy matrix into a crisp matrix, or you have to convert a fuzzy number into a crisp number. So these are all the methods that you can use for doing this, right? So the methods that we have are max membership principle, centroid method, weighted average method, mean max membership, center of sums, center of largest area, first of maximum and last of maxima. So let us see how these methods actually work. So the first one is called the max membership principle. So what you have to do is you have to look at the height of your membership value. Okay, so the membership function that you have with the continuous membership value that you have to find the peak output of that. In other words, the value which has the highest membership value. Okay, and that will give you the max. So you are representing this entire membership function by that particular membership value. Okay, so mu c x bar equals greater than or equal to mu c of x. So the one which gives you the maximum. So if we look at this particular membership function, this would be your, so the output you are getting is the x bar, x star here. So x star is the one which has the maximum membership value over here. Okay, the second method is called the centroid method. So in the centroid method, you are taking the center of mass, okay, or it's called the center of area or the center of gravity method. Okay, that is, you take the membership value, multiply it by the x at that particular membership value and divide it by the addition of all the membership values that you have. Okay, that is actually equivalent to what is done here. Okay, so this is done in a continuous manner, whereas this is a discrete manner, right? So you take every single xi value, multiply it by membership of that and divide it by the aggregate of all the membership values that you have. Okay, so if we take this, the second method would give something like this as a centroid. So it's something like finding the centroid of this curve that you have basically. Okay, and the third one is to take the weighted average method. Okay, so you take the points which have the maximum output and then find the middle of that. Okay, so yeah, so here actually there are two membership functions. So this is one membership function, this is another membership function. So you are finding the element, this is one of the elements, this is the other of the two elements that you have, and you are going to take this as your defuzzified output to give your x star basically. The next method is called the mean max membership. So this is known as the middle of the maxima. So you find the maxima. So if we take the figure here, okay, you find this is the maximum that you are having. So you take this entire all these values and find the middle value of that, okay, and that will be the x star that you are going to take. So x star is equal to, if you take everything which is the maximum that you have, all those values, and you add them up together, divide by n if you have n such values. So it's equivalent to saying you take, if this is a and this is b, you take a plus b by 2, which will give your middle value over here, okay, which is the x star that you are basically looking for. The next method is called the center of sums. This employs the algebraic sum of the individual fuzzy sets instead of their union. Okay, so you are taking the sums of these individual fuzzy sets. Okay. So the fifth, so this gives you the thing. So this is your, if you have two fuzzy sets, okay, this gives you the center of sum. So you are taking the union, the intersection of the two, and then finding the center of sums for that. So this gives you your x bar for that. Then the next method, basically center of largest area. So what happens here is, if you have say two subsets or more than two subsets which are not sort of intersecting each other, no. So you have one subset, another subset, etc. You find the subset which has the largest area, right, and find the center of that basically. So here if you have a membership function in this way, you could say this consists of two subsets, okay, this is one subset and this is the other subset, and you find that this is the one with the larger area. So you take this subset and find the center of that, okay, the center of gravity. So this is known as the center of largest area method. Then the next one is the first of the maxima or the last of maxima. So basically you are finding all the maximum points, right. So if we have something like this, you are finding, you may have more functions also. You find this will be one maxima, this will be another maxima, you may get another maxima, etc. And after you do that, you find the first of those. Okay, so here you are saying the maximum height in the union is found, okay, and then you find all the values which come into this one, okay. Once you have found that, you find the first of the maxima. So all the maxima that you have found, you take the first out of that, okay, the greatest lowest bound, okay, and you can also find the last one. So here this is if you say this is the last one, okay, you can find the maxima of that, and that will give you the value that you are actually looking for, okay. So these are all different methods for doing defuzzification. So finally you have to carry out defuzzification, and finally you have to do the fuzzy inference system, okay. How does the fuzzy inference system work? Okay, so we have seen parts of it, we have seen how you do fuzzification, we have seen how you have if then rules, etc. So let us see what all is there in the fuzzy inference system. So you have first of all a rule base which will consist of if then rules, right? And you have a database here, and this database basically holds the membership values for all the variables which you are using in your rule base basically. Okay. So you have a rule base which contains fuzzy if then rules, and you have a database which defines the membership functions of fuzzy sets which are used in the fuzzy rules. Then we have the decision making unit which actually makes the decision on what is your output, right? And then we have the fuzzification interface unit that converts crisp quantities into fuzzy quantities, and you have the defuzzification interface. So whatever decision you are making, you are getting a fuzzy value, and you are going to carry out defuzzification here to get your crisp output basically. Okay, and this is your input which is being fuzzified basically over here. So these are what is finally happening. Okay. So this rule base and the database which contains all the membership values together is known as your knowledge base basically. So there are two methods of the inference systems. Okay, one is what is called the Mamdani method. So in the Mamdani method, what you are basically doing is that you are getting the output as membership values which need to be combined basically. Okay, and these are combined to form again membership values which are fuzzy, right? And these are combined together by using fuzzy combinations like union, intersection, all those type of things. And finally the output you are getting could be something like this, right? A fuzzy output. And then defuzzification will be carried out on that to get your overall crisp output. The next type is what is called the Sugeno fuzzy inference system. So here it uses the fuzzy rule is if x is a and y is b, then z is equal to fxy. So here a and b are the fuzzy sets which you have, and z will be the crisp function that you are basically looking for. Okay. So you are taking two values from the fuzzy sets and you are combining them with the crisp function basically. Okay. So that will be something like this. You have two membership functions inputs and you are taking the x and y from there and you are putting it into z, which is a function of x and y, to give a crisp output basically. So that's how this Sugeno rule will actually work. So these are the two methods. Okay, so we have the fuzzy inference system like this, but the way in which you are doing the defuzzification or the fuzzification and the defuzzification of the output from the decision making unit is different in the two methods, so that you get two different outputs. So we'll stop the so that is the fuzzy sets and fuzzy inference, which in fact the book contains a whole lot of problems which you could actually go through. So we'll stop at this stage.